In this video, we're going to take a deep dive into some of the world's most powerful military weapons. We'll examine the historical context of how these systems came to be, the cutting-edge technology that makes them so formidable, and the strategic roles they serve on the modern battlefield. We'll discuss stealth aircraft marvels of aerospace engineering that can outsmart conventional radar. We'll talk about railguns that exploit electromagnetic forces to hurl projectiles at breathtaking speeds. We'll explore comprehensive air defense systems with pinpoint targeting capabilities, as well as many other impressive examples of modern military might. From the earliest prototypes to the futuristic concepts on the horizon, we'll shine a light on how scientific breakthroughs shape the global balance of power. By the end of this video, you'll see not only how these weapons work and why they're so crucial, but also the complexity, innovation, and sometimes moral quandaries that envelop their existence. Before we jump into the details of these remarkable machines, I want to take a moment to welcome both new and returning viewers to this channel. If you enjoy deep dives into technology, military history, and the way science shapes our everyday lives, you've come to the right place. Every like, comment, and subscription helps this channel reach more people, and it lets me know that you're enjoying the content. So if you haven't already, consider subscribing and hitting the notification bell to stay updated on all future episodes. And if you find something interesting or have a thought to share at any point during this video, please leave a comment. Also, smash that like button to let the algorithm know we're doing a good job. It really helps the channel grow, and I appreciate your support. Now let's get comfortable and prepare to journey through some of the most extraordinary feats of modern military technology. We'll start by exploring the ever-evolving concept of stealth. Concealing movement has been a cornerstone of military strategy since time immemorial, from camouflage on the ground to submarines beneath the waves. But perhaps nowhere is stealth more groundbreaking than in the skies, where detection usually spells disaster. Let's roll up our sleeves and dig in. Stealth technology, in broad terms, aims to make an aircraft less detectable by radar, infrared, sonar, and other detection methods. This concept has deep roots. Historians can point to camouflage paint, or even special flight paths used during World War II as early attempts at stealth. However, the real leap happened during the latter stages of the Cold War, when advanced radar systems started to dramatically improve. In response, aviation engineers embarked on designing planes with features that minimized radar signatures. At the heart of modern stealth aircraft is a balance between shape, materials, and special coatings. Each of these elements is meticulously engineered to reduce an aircraft's radar cross-section. First, the shape. Stealth aircraft often feature angular or faceted designs, as seen in the F-117 Nighthawk, or curved surfaces that deflect radar waves away from the source, as seen in the B-2 Spirit. These shapes don't just look futuristic, they're mathematically optimized to scatter radar signals. Next, the materials. Carbon composites and radar-absorbent materials are used in construction to dampen the electromagnetic waves emitted by enemy radar. Lastly, we have specialized coatings that can further absorb or diffract radar energy. These coatings are often extremely sensitive to environmental factors, making them costly and challenging to maintain. One of the crown jewels of modern stealth technology is the F-22 Raptor. Its design approach prioritizes reducing its radar signature from nearly every angle, giving it a pronounced advantage in first-strike scenarios. The pilot can often see the enemy before the enemy sees them, which is critical in air-to-air combat. The F-35 Lightning II is another product of this stealth revolution, though it had to balance stealth capabilities with affordability and the ability to be deployed across multiple branches of the U.S. military. These planes combine stealth with supersonic flight, advanced avionics, and data fusion systems that provide pilots with an unparalleled picture of the battlefield. But stealth isn't just about radar. Modern sensors can rely on infrared signatures as well, so stealth aircraft must reduce heat emissions from their engines. Technology such as cooled exhaust, special engine placement, and even the control of flight paths can help mitigate infrared detection. The aircraft also employ techniques to minimize radio transmissions that could be intercepted by enemy forces. The result is a high-tech marvel that can operate in hostile airspace with a lower risk of detection. Stealth isn't infallible, though. Over time, countermeasures have emerged. Advanced radar systems can leverage multiple frequencies and detection methods. There's also the risk of detection through advanced infrared tracking systems that pick up engine heat from greater distances. The cat-and-mouse game between stealth and detection technologies continues to push innovation in both domains. Nonetheless, stealth aircraft remain some of the most formidable tools in a modern arsenal, redefining how air superiority is achieved and maintained. Next up in our survey of modern military marvels is the railgun, a device that has captured the popular imagination for years. Railguns operate on a principle of electromagnetic force. Instead of using traditional chemical propellants like gunpowder, a railgun uses a powerful electrical current that flows through two parallel conductive rails, creating a magnetic field that accelerates a projectile along the rails at extremely high speeds. The velocity that railguns can achieve is astounding. A conventional tank round might travel at speeds around 1.5 kilometers per second, while a railgun projectile can theoretically reach speeds upwards of 6 or even 7 kilometers per second. The kinetic energy from this speed alone means the impact can be devastating without the need for an explosive warhead. Imagine hitting a target with such force that the projectile effectively vaporizes on impact and transfers a massive amount of kinetic energy to the target. That's what makes railguns so appealing from a military standpoint. Development of railguns has been primarily spearheaded by nations with significant scientific and financial resources, particularly the United States and China. One of the big challenges has been power supply. Generating the enormous amount of electrical energy needed to accelerate a projectile to hypersonic speeds is no small feat, especially in mobile platforms like ships. In tests, prototypes have demonstrated successful launches, sometimes reaching muzzle energies that dwarf conventional naval artillery. However, wear and tear on the railgun's internal components has proven problematic. The rails and armature undergo significant stress due to the intense electromagnetic forces, causing them to erode or deform rapidly. Despite these challenges, the potential advantages are immense. A railgun projectile costs significantly less than a guided missile, while traveling at speeds that make interception extremely difficult. Additionally, the absence of a traditional explosive warhead reduces safety risks during transportation and storage. The research continues, and while widespread deployment of railguns on modern warships or land-based platforms has yet to become a reality, it's clear that the technology has the potential to redefine naval and possibly land-based artillery if the engineering hurdles can be overcome. No discussion about powerful military weapons would be complete without exploring modern air defense systems. While stealth aircraft are designed to evade detection, advanced air defense networks aim to spot and neutralize incoming threats at distances that were unthinkable mere decades ago. At the core of a robust air defense system is the radar array. Modern radars can scan vast distances, track multiple targets simultaneously, and even differentiate between aircraft, missiles, and decoys. Systems such as the Russian S-400 and the American Patriot PAC-3 exemplify this capability. They employ phased array radars that can guide multiple interceptors toward multiple targets at once, sometimes even engaging ballistic missiles in their descent phase. The interceptors themselves are engineering marvels. They must be agile, extremely fast, and equipped with guidance systems that can lock onto a moving target in real time. In some cases, these interceptors carry proximity warheads designed to detonate near the target, shredding it with shrapnel. In others, as with many ballistic missile interceptors, they rely on kinetic impact, essentially hitting a bullet with a bullet. Precision is the name of the game here. A minuscule deviation in trajectory can mean a miss over distances of tens or hundreds of miles. Air defense systems also rely on advanced command and control networks. They fuse data from multiple radar installations, satellites, and even reconnaissance aircraft to build a comprehensive picture of the airspace. This information is shared with interceptors and fighter jets in real time, allowing for a coordinated response to aerial threats. In the modern era, the synergy between these systems can effectively create a layered defense. Short-range systems protect against low-flying or immediate threats, medium-range systems address intermediate distances, and long-range systems like the S-400 or terminal high-altitude area defense handle ballistic missiles or high-flying targets far from their territory. The sophistication of these networks creates a constant challenge for would-be adversaries. Even stealth aircraft have to adapt, as advanced radars and detection methods can compromise stealth advantages. As such, air defense systems are a key pillar in many nations' national security strategies, effectively deterring or defending against aerial attacks. The race to develop hypersonic weapons is another front in the quest for military dominance. Hypersonic missiles travel at speeds of Mach 5 or greater and can maneuver unpredictably, making them exceedingly difficult to intercept. Traditional ballistic missiles also achieve high speeds, but they follow more predictable trajectories. Hypersonic vehicles, by contrast, can execute evasive maneuvers throughout their flight, challenging the current generation of missile defenses. There are two primary types of hypersonic weapons: hypersonic glide vehicles and hypersonic cruise missiles. An HGV is typically launched via a rocket booster to near-space altitudes, where it then glides at hypersonic speeds toward its target. A hypersonic cruise missile, on the other hand, usually employs an air-breathing scramjet engine to sustain flight at these extraordinary velocities within the atmosphere. The United States, China, and Russia are key players in hypersonic research. Russia's Avangard HGV, for instance, has been reported to reach speeds up to Mach 27. China has tested various HGV prototypes, and the U.S. is developing systems such as the AGM-183 air-launched rapid response weapon. The engineering challenges are immense. Controlling and cooling a vehicle traveling at such speeds generates extreme heat, often exceeding 1,000 degrees Celsius, on the vehicle's surface. Materials that can withstand and dissipate this heat must be developed, and the guidance systems must be extraordinarily robust to maintain accuracy at extreme velocity. The strategic implications are profound. A hypersonic weapon can shorten the decision-making window for defense, as it could potentially reach targets thousands of miles away in mere minutes. Moreover, its ability to maneuver at high speeds complicates interception. This has sparked concerns about a new arms race and the destabilizing effect such weapons might have on global security. Regardless, hypersonics represent a major leap in offensive capability and remain a hotbed of research and development. When we think of directed energy weapons, it's easy to conjure up images from science fiction, lasers slicing through the hulls of starships. Yet, directed energy weapons, primarily high-energy lasers and high-power microwaves, are increasingly crossing the threshold from experimental technology to deployable systems. Lasers, in particular, have become a focus for militaries seeking precision weapons with potentially limitless ammunition, as long as you have power. High-energy lasers concentrate photons onto a target, heating it to critical temperatures. This can disable or destroy drones, small boats, or incoming missiles. The advantage is the speed of light engagement. There's no time of flight for a laser beam, making evasion incredibly difficult for targets within line of sight. The cost per shot is also significantly lower compared to conventional munitions. One main challenge, however, is maintaining beam quality over distance. Dust, smoke, clouds, and atmospheric turbulence can degrade the beam, reducing its effective range. The U.S. Navy has tested laser systems on ships such as the Laser Weapon System, which has shown promise in neutralizing small threats. Other nations are also exploring their own directed energy programs. High-power microwave weapons, meanwhile, target electronic systems, frying circuits, and communications. The fundamental physical principles are sound, but many hurdles remain for large-scale deployment, including power generation, cooling, and reliability under battlefield conditions. Despite these challenges, directed energy weapons stand to revolutionize warfare. They could become a viable way to intercept missiles or drones cheaply and quickly, reshaping both offensive and defensive military strategies in the coming decades. Stealth jets, railguns, hypersonic missiles all are game changers, but another transformative technology in modern warfare is the proliferation of unmanned aerial vehicles, or drones. Once limited to reconnaissance roles, drones are now used for targeted strikes, loitering munitions, and even electronic warfare. They come in all shapes and sizes, from small quadcopters used by infantry units for situational awareness, to large long-endurance systems like the MQ-9 Reaper. Combat drones have several advantages. They remove the need for an onboard pilot, allowing more daring or extended missions without risking human life. They can loiter for hours or even days, providing valuable intelligence and striking targets of opportunity as they arise. Many feature advanced sensors, from high-resolution day-night cameras to synthetic aperture radar and signals intelligence packages. The data they gather can be streamed back to command centers in real time. Armed drones typically carry precision-guided munitions, such as Hellfire missiles. These weapons can strike targets with remarkable accuracy, minimizing collateral damage. However, their use is not without controversy, as drone strikes have generated significant debate about ethics, civilian casualties, and the ease with which force can be deployed. On the battlefield, drones have proven useful not just for strikes, but also for swarming tactics. In these scenarios, a large number of low-cost drones coordinate to overwhelm enemy defenses. As artificial intelligence advances, future drones may become increasingly autonomous, capable of making decisions independently, an unsettling prospect for many observers who worry about the moral implications of autonomous killing machines. Land and air might get much of the spotlight, but control of the seas remains a cornerstone of projecting military power. Aircraft carriers, often dubbed floating cities, are among the most visible and potent symbols of naval might. A Nimitz-class or Ford-class U.S. aircraft carrier can deploy dozens of aircraft, from fighters to helicopters and support planes, effectively serving as a mobile airbase that can be positioned anywhere there is water. The sheer size, combined with the nuclear reactors powering these behemoths, allows them to operate for extended periods without refueling. Carriers function as a centerpiece of a carrier strike group, which includes destroyers, cruisers, and submarines that defend against air, surface, and underwater threats. Submarines, especially nuclear-powered ballistic missile submarines, play a more concealed but equally critical role. These vessels can remain submerged for months, making them a stealthy and survivable component of a nation's nuclear triad. They carry intercontinental ballistic missiles with multiple warheads capable of launching strikes from under the sea. Attack submarines, on the other hand, specialize in hunting enemy submarines and surface ships, as well as conducting intelligence-gathering missions. Modern navies also feature advanced surface combatants like guided missile destroyers and cruisers. These ships come equipped with the latest in phased array radars, vertical launch systems for missiles, and sophisticated electronic warfare suites. With the advent of long-range anti-ship missiles and hypersonic threats, naval warfare is undergoing a transformation that mirrors the challenges seen in aerial and ground domains. Stealth design is making its way into naval vessels as well, with certain ships featuring angled superstructures and radar-absorbent materials to reduce their radar cross-section. While air power often grabs headlines, tanks and armored vehicles continue to be indispensable on the ground. The main battle tank remains a key player in combined arms operations, offering firepower, mobility, and protection for ground forces. Iconic MBTs such as the M1 Abrams, the T-90, the Leopard 2, or the Challenger 2 have shaped armored warfare doctrines worldwide. Modern tank designs focus on sophisticated armor systems, including composite armors that blend ceramics, steel, and other materials to defeat kinetic and shaped charge threats. Many also incorporate explosive reactive armor that detonates on impact to disrupt incoming projectiles. Active protection systems are the latest evolution, detecting and intercepting incoming anti-tank missiles with small countermeasures before they can strike the vehicle. The gun, typically a 120mm or 125mm smoothbore cannon in modern main battle tanks, is capable of firing a variety of rounds, from armor-piercing fin-stabilized discarding sabot to high-explosive anti-tank shells. Advanced fire control systems with thermal imaging, laser rangefinders, and ballistic computers enable main battle tanks to engage targets accurately, even while on the move. Innovation in armored warfare is ongoing. Some concepts explore unmanned or remote-controlled tanks, while others focus on hybrid electric powertrains to reduce thermal and acoustic signatures. As anti-tank weapons evolve, so too must the defenses and offensive capabilities of MBTs, ensuring a continued push toward more advanced, integrated, and survivable vehicle designs. Physical weapons like stealth aircraft, railguns, and tanks might capture our imagination with their sheer firepower, but there's a quieter battlefield that's becoming increasingly important: the digital realm. Cyber warfare can be every bit as destructive to military systems as a physical attack, targeting communication networks, power grids, and logistics systems. Sophisticated malware can disrupt command and control, while hacking attempts might steal classified information or sabotage critical infrastructure. Although not a weapon in the traditional sense, the ability to cripple an opponent's cyber infrastructure can have a profound impact on their overall military effectiveness. Many nations now consider cyber capabilities a core component of their defense strategies. Cyber command units work to secure their own networks and potentially carry out offensive operations against adversaries. The lines blur here, since the same code that defends can also be used to attack depending on the situation. The challenge is that attribution can be murky, making escalation and retaliation tricky geopolitical endeavors. In a future conflict, the initial salvo might not be a missile launch, but a preemptive cyber strike aimed at blinding early warning systems or disabling critical defenses. Thus, militaries worldwide invest heavily in both cyber offense and defense to maintain an advantage in this emerging domain. Artillery has been a staple of warfare for centuries, and modern developments have turned it into a high-tech affair. Systems like the M142 HIMARS can launch precision-guided rockets and missiles at targets up to 300 kilometers away. These advanced systems use GPS guidance and inertial navigation to achieve pinpoint accuracy, effectively removing the traditional limitations associated with artillery. Meanwhile, ballistic missiles remain a key strategic asset, capable of delivering conventional or nuclear payloads over vast distances. Nations with intercontinental ballistic missiles can hold potential adversaries at risk halfway around the globe. The complexity of these systems lies in their propulsion, guidance, and re-entry vehicles, which must withstand immense heat and pressure. Over the years, arms control agreements have tried to regulate the proliferation and testing of long-range missiles, recognizing their devastating potential. Cruise missiles like the Tomahawk or the Caliber also play a vital role in modern warfare. These can be launched from ships, submarines, aircraft, or land-based platforms, and can navigate via terrain mapping, GPS, and inertial guidance to strike targets with exceptional accuracy. The versatility and range of these systems make them indispensable for striking heavily defended or distant targets without risking manned aircraft. As fascinating as these powerful weapons are from a technological standpoint, they come with weighty moral and ethical questions. The destructive potential of stealth bombers, railguns, and hypersonic missiles raises concerns about collateral damage and the escalation of conflicts into all-out war. The increasing autonomy in systems like drones leads to debates about accountability and the threshold for using lethal force. Directed energy weapons, cyber warfare, and ballistic missiles each have their own sets of dilemmas, from the possibility of indiscriminate disruption to the existential threat of nuclear confrontation. The quest for more advanced weapons is often fueled by deterrence. If an adversary knows you possess an unbeatable military edge, they might hesitate to engage. Yet this arms race can lead to a cycle where each new technology is matched by a counter-technology, pushing global tensions to precarious levels. The hope is that through international treaties, diplomacy, and cooperation, humanity can manage these destructive capabilities responsibly. But the reality is that as long as nation-states exist, competition in military technology is likely to persist. We've journeyed across the skies, beneath the seas, and into the digital realm to explore some of the world's most powerful military weapons. From stealth aircraft designed to be invisible to radar, to railguns that utilize electromagnetic force for incredible projectile speeds, to the air defense systems that tirelessly scan the skies, the sheer scope of human ingenuity and military technology is breathtaking. We've seen how hypersonic weapons can strike with terrifying speed, how directed energy weapons are turning science fiction into reality, and how drones have redefined surveillance and combat. On the seas, massive aircraft carriers and elusive submarines project power across the globe, while on the ground, tanks and artillery demonstrate that raw firepower still has a vital place on the battlefield. And let's not forget the invisible, but increasingly important domain of cyber warfare, where lines of code can be as lethal to an enemy's infrastructure as any missile. As we look to the future, the pace of technological advancement suggests even more revolutionary capabilities on the horizon. Quantum computing might break modern encryption methods, artificial intelligence may enable swarms of autonomous weapons, and new materials could radically change the performance of existing platforms. The ethical and strategic implications will undoubtedly grow more complex. It's a fascinating and, at times, unsettling glimpse into the possibilities of human innovation when applied to warfare. If you made it this far, thank you for watching and learning with me. I hope this exploration has sparked your curiosity about the interplay between technology and military strategy. If you enjoyed this deep dive, please consider liking this video. It goes a long way in supporting the channel. And if you haven't subscribed yet, now's the perfect time. Hit that subscribe button and ring the notification bell so you don't miss any of our future episodes. We cover everything, from the evolution of warfare to cutting-edge scientific breakthroughs and beyond. Also, I'd love to hear your thoughts on today's topic. Feel free to leave a comment below. Which weapon system do you find most intriguing or concerning, and why? Let's keep the conversation going in the comments section. See you in the next video.